Okay, calculus people, here we go into section 2.8, which is the last section that we are going to cover in chapter 2. And it's not too bad of a section, everybody. In fact, you won't see this very often. I think I've only got 4 slides to cover with you here, and they're pretty short ones at that. Now, the intermediate value theorem is the first of 3 big theorems that we are going to cover in the first semester of AP Calculus this year, going along with the extreme value theorem and the mean value theorem, but both of those show up in chapter 4, so we've got some time until we get to the others. When we're studying for our first semester final towards the end of December, everybody, if we're taking finals, we'll see how that goes, you'll hear me talk about then the 3 big theorems that we covered in the first semester, and this is the first one of them. So, to break it down here, the name intermediate should tell you something already. We're dealing with something numerically that's in the middle between 2 other things, and that's kind of what the intermediate value theorem deals with. So, the IVT, as the cool kids call it, everybody, says the following. Now, I hate to sound like a geometry teacher. I know this was 3 years in the past for you guys, but I really do think it behooves us, ladies and gentlemen, to think about this theorem in terms of the if-then format that you guys were used to seeing back in geometry in chapter 2, how most of your theorems then were written. The if is the hypothesis of your theorem, and all of these conditions in the hypothesis need to be met. Let me finish my sentence now, in order for the conclusion to be valid and meaningful. So, the intermediate value theorem only is applicable to us if 3 things happen here. And the first one, of course, is the big one. If your function, f of x, is continuous on a closed interval from a to b. We've been talking a lot about continuity within this particular chapter here, guys. So, the function that we're dealing with has to be continuous on this interval from a to b, meaning that it cannot have any holes, any jumps, or any asymptotes at any x value in between a and b, including at a and b itself. So for this to happen, the function might need to do something like this, or it could be boring and just do something like that, but it cannot do something like this, everybody, where let's say there's a whole empty spot right there, and then do something like this. So the first one that I drew works, the second one that I drew works, the third one has a jump discontinuity somewhere in the middle of it, so that one would not apply. We'll get to that a little bit more later. But this only applies if your function is continuous on this closed interval from a to b. And then the second 2 conditions here basically just tell us the y values that this function begins and ends at on this interval here from a to b. So we randomly are saying that f of a is equal to m and f of b is equal to n. Let me stop for just a second and point out something that I hope you guys know, although I'm not sure that you do. When variables are used within the definitions of theorems or formulas or anything like that, the existence of a new variable actually tells you something new. Let me show you what I mean right here. When we first said f of x needs to be continuous on this closed interval from a to b, that's the first mention of the numbers a and b, which really seems to suggest that they can be any real numbers that we want them to be. The only important thing to take from that is because of the way that we use interval notation, we do know for a fact, everybody, that a is the left endpoint and b is the right endpoint, and that tells us for a fact that a has to be less than b. You would never see an interval written such as like 5, 2. That doesn't make any sense, and that's not a valid way of writing an interval. So the a and the b are new numbers, and we're just supposed to assume that they are real numbers, and they follow this pattern that a has to be less than b. But now when we've used the a second time, that's indicative of the fact that that a is not a new number, that it has to reference the left endpoint of the interval where we're looking at right now. But what's important here is that m now is introduced as a new variable, and that tells us that m is in no way related to anything that we have discussed before, which kind of implies that m could be any real number. Now again, here's b, the right endpoint being used again now, but n is a new value as well. So anyhow, guys, these are the three conditions here for the hypothesis in order for the intermediate value theorem to apply. First, your function has to be continuous on the interval from a to b, and then we need to know that f of a is equal to m and f of b is equal to n. Really, it's that first one that's the important condition of the hypothesis. The other two just kind of tag along. But now the then, everybody, the big conclusion, the payoff of this theorem. If all of those things in blue happen, then we know that what is said in red here has to happen as well. And the conclusion of the IVT says that every single y value in between m and n. And remember, guys, m was the starting y value of this function, and n was the ending y value of this function. So every single y value in between those two y values, m and n, must occur at least once within the range of this function. And furthermore, the location of that y value right there has to occur at some x value that we kind of generically call c, and it does say here that c needs to be located in between a and b. Ta-da! That's it, everybody. Now, what I think this probably indicates is the idea that even for smarty pants people like yourselves who are in AP Calculus, reading mathematical theories and concepts and postulates isn't really all that useful to us until we have a picture to kind of illustrate what's happening. So if you're a little confused as to what in the world Mr. Fontana's been talking about for the last 5 minutes, I get it. I would be too in your situation. So let's try to draw a really simple graph of what's going on right here. Okay, so if I go back to the hypothesis of the intermediate value theorem, this is something I tell my geometry kids all the time, the hypothesis really tells you what you need to be drawing in your diagram. So the hypothesis here told us that we needed to have a continuous function on a closed interval from a to b. Now we knew for a fact, because of the way the interval a to b was written, we knew that a had to be less than b, so the order of these two numbers right here is locked into place. We know that a is the left endpoint is b and b is the right. What we don't know, that I have assumed with my little graph right here, is that if in fact this is the origin, I'm suggesting with this graph that a and b are both positive values. That is absolutely not the case, and it doesn't say that anywhere in the hypothesis or the conclusion of the IVT. So that's just something for simplicity's sake that we've assumed, but that doesn't need to be the case. Now, here's what's going on, guys. In order to satisfy the hypothesis of this theorem, I'm actually going to talk about the three conditions out of order a little bit. I'm going to start with the second one right here. Very simply, f of a is equal to m. So I've randomly put m somewhere on my y-axis. A is here on my x-axis. And for f of a to equal m, there's got to be a point right there, and that's what I'm going to consider the starting point of my graph. F of a is equal to m. The third condition, this one right here, said that f of b has to equal n. So I move over to b on my x-axis, up to n on my y-axis, and now what we've got right there is what I'm going to call the ending point of this particular function. And now the important part, everybody, let me go back to the first condition right here. F of x, now I'm going to stop right there, guys. That in and of itself says something important. We are using function notation right there. So that implies, everybody, that we must be dealing with something that is a function. Okay, a relation in which each x value is paired with one and only one y value. So what we're about to draw must be a function, and that's important. And furthermore, if I keep reading that first line, this function has to be continuous on the closed interval from a to b. So that means it needs to both begin and end with a solid dot, not an open dot, in order to be left continuous at b and right continuous at a. And going along with that, everybody, we need to draw something that's continuous between those 2 points, meaning no holes, no jumps, and no asymptotes. So on your homework, guys, I made a worksheet for you guys to work on for the 2-8, this intermediate value theorem concept. And at the very top of that, I gave you guys like room to draw 4 really quick graphs. I basically wanted you to start these around here, something like this, and then just get creative in the way that you draw them. Okay, so to make a point here, everybody, I'm going to go ahead and draw what's kind of an interesting curve here. I'm going to make this thing go down a little bit from that point and then back up and then stop and end at that ordered pair right there. So what I have drawn right now is absolutely not the only way to draw this graph, but I believe that what I've done satisfies the three conditions of the intermediate value theorem. I have drawn a function. It is continuous on the interval from a to b. F of a is equal to m, and f of b is equal to n. So this is one of an infinite number of graphs that we've drawn here that could work. Okay, so now that we have a diagram here, a graph that does illustrate the hypothesis, let's talk about the conclusion. The then statement, everybody, of the intermediate value theorem says that if all of this stuff up here happens, which it did, now let's start working here. Every single y value in between m and n must occur at least once. All right, so if I go back to this graph, if I were to choose a random y value in between m and n, so I'm going to go right over here and I'm going to call that p. The intermediate value theorem tells me that this function has to have a y value of p that occurs at least one time. And if I shoot this little line horizontally straight across over here, that would be the line y is equal to p. Sure enough, you guys, we see that that line does cross the curve itself. So the intermediate value theorem guarantees us the existence of at least one point on this graph where your y value is equal to p. It actually could have been more than that. Let me do this in green. I'm going to erase this as soon as I do it. But if I had made this graph a little bit different, maybe it had done something like that. Ignore what's in black. In fact, let me get rid of that for just a second. If I get rid of that completely, there you go. Now in this case, that y value of p actually occurs 5 times on this graph right here. So remember, a function has to pass the vertical line test, but it doesn't have to pass the horizontal line test to be a function. It does to be one-to-one, but that's not what we're talking about here at all. So that's the significance of that phrase, at least once. It could happen more than that, although it certainly doesn't have to. So let me get rid of all that. Oh, before I do that though, when you guys work on the 2.8 worksheet then, and you have the opportunity to draw some interesting graphs up there at the top, okay, you might want to draw at least one of yours to be a little bit interesting like this and not be a one-to-one function. That might help you on some of those yes or no questions that I asked you before. So back to where we were here. Let's get to it one more time because I want to finish something else up. So the conclusion of the if-then statement right there said that your y value, p, located in between m and n, had to occur at least once. But if we go further with that, the location of that point is also something we know. From that point, if I were to drop straight down now to my x-axis, I get a value right here that we called c. And it must be the case, everybody, that c has to be located in between a and b. Okay, so that right there, guys, is kind of what the intermediate value theorem tells us. Now, obviously, this works for any y value that we choose in between m and n. I could go a little bit higher over here, and I guess I could call that, I don't think you need to put this in your notes, but I could do this with q. I shoot straight over to the right. Sure enough, I hit the curve. I come down with it now, and there's maybe an x value that I'm going to call d, and sure enough, d is between a and b as well. I could do another one right over here. Let me call that r. And if I shoot this one to the right, everybody, there we go. Yep, it hits the curve. And where? At an x value now that I'll call e, that is once again in between a and b. Now, what I want to make sure everybody understands is that there are y values right here in this curve. Like, for example, maybe right up here, there's a y value right here that is not in between m and n. The intermediate value theorem doesn't say anything about y values that occur outside of the range from m to n. They might occur, they might not occur. The theorem isn't saying anything about that. It is only saying, everybody, that if you've got a y value in between m and n, that y value has to occur at least one time on this interval. So the intermediate value theorem essentially says, you guys, we can't skip y values. If you started right here with a y value of m and you ended right here with a y value of n, every single y value now between m and n must occur at least once. The only way that couldn't happen is if you had a function that was not continuous on that interval, and that's not where the intermediate value theorem applies. All right, so what are we supposed to do with that? I've really got one quick question to run through with you guys here to kind of show you how the IVT works and how it applies, but it's not all that complicated. So here's the question. Is any number 1 less than its cube? And we're supposed to use the intermediate value theorem to justify our answer. Okay, so as we start thinking about numbers and their cubes, I think we're going to find right here that this is maybe a little bit tricky here, guys, if we start thinking just about x's and y values right here. So if I were to make a quick little column right here of x values and then a y value, that was the cube of our x value. The way I'm doing this right now, guys, is really not the way I want you to handle it, but let's go ahead and just think about it. I'm trying to illustrate the shortcomings right now of what is really kind of a juvenile way of reasoning, saying that something must only exist if I can see it or if I can find it. And I don't think we're going to like what we see here. If I let x equal 0, the cube of 0 is 0. So in that case, that number is equal to its cube. That's not what we're looking for. Okay? 1 is also equal to its cube. So that's no good. 2 has a cube of 8. So that number, 2, is 6 less than its cube, 8. That's not what we were looking for. We were looking for something to be 1 less than its cube. Okay, so these numbers here, the gap wasn't big enough. The gap was 0. All of a sudden, the gap just jumped up to a 6. And I think if I go any further, we're not going to like what we see. If I cube 3, I get 27. Oh man, and that number's 24 less than its cube. So that didn't work either. Okay, so we were not able to find an integer, or really any number for that matter, that was exactly 1 less than its cube. And that's usually going to be the case, guys. Otherwise, this would be a really boring problem. So let me get rid of all of that junk right here, because that's really not the way we're going to approach these problems. What we're going to try to do instead is to be systematic about it, to be mathematical about it, and to try to use this theorem that we've just learned to try to justify something happening or not happening. So the first thing we're going to do, we're going to make an equation out of this question right here. Is any number 1 less than its cube? Well, the number itself we're going to call x. And of course, we have an is right there. We want to know, is there a number, x, that is 1 less than its cube? And the way we would express that, let me go back to Algebra 1. There's the cube, and 1 less than that would be to put a -1 at the end here. So is there any number, x, that is x cubed minus 1 means 1 less than its cube. So the question here is, everybody, does this equation have a solution? If it does, then the answer to our question is yes. If it doesn't, then the answer to our question is no. And the way we go about proving this is to try now to move all of our terms to one side or the other and to make a function out of this. I'm going to bring this x over here to the other side. Okay, and what we're going to get then is x, let me do it this way. Let me go ahead and write this as a function of x, which is now going to be x cubed minus x minus 1. And my question is, will that function right there ever take on a value of 0? That's what happens right here, guys, when we subtract an x from the left and we subtract an x from the right. This side over here becomes that 0. So it's the same question, just kind of phrased a little bit differently now. Can I ever get this expression, x cubed minus x minus 1, can I ever get it to equal 0? Now, if we were to just hunt and peck right here and once again try to find the number, we're not going to come up with it. But what we can do, as I said, is to try to be a little bit systematic. So I'm going to go ahead, and this is going to look similar to what I did a second ago. I start with 0 just because it's the easiest number in the world to work with. And when I plug 0 in for x here, I end up with 0 minus 1, and that gets me a -1. I wanted something to equal 0, so guess what? I didn't find it. Let's keep going. F of 1. And I chose 1 just because 1 is the second easiest number to work with. 1 minus 1 again gets me -1. And once again, I did not find the 0 that I was looking for. So I keep going. And now let's see what happens when we plug in a 2. 2 cubed is 8, minus 2 is 6, minus 1 is 5. That is also not the 0 that I was looking for, but something significant just happened. What happened here, guys, in the last two values that we tested, is that we just went from a y value of -1, which obviously is less than 0, to a y value of 5, which obviously is greater than 0. And since the function that we're dealing with right here is a polynomial, we know that all polynomial functions are continuous for all values of x, for every real number. So let's clarify. We are dealing right here, everybody, with a continuous function on really the interval of all real numbers. So we have a continuous function. Right here, this is our f of a is equal to m. Okay, in fact, let me write that. There's your a value, there's your m value. And then right underneath that, 2 would be our b value, and 5 would be our n value. And the significance right here, everybody, is that our y values just jumped from a negative number to a positive number. Now, the intermediate value theorem applies, basically, because this function is continuous. And we knew the starting value of -1, the starting y value, and the ending y value of 5. And the conclusion of the intermediate value theorem tells us that if all of this stuff happens, every single y value in between -1 and +5 must occur at least once. And what's the one significant y value we wanted to have happen? 0. So somewhere in between these two data sets right here, guys, there's got to be some value out there. I don't know what the x value is, so I'm just going to call it c. And f of c has to equal a y value in between -1 and 5, including the y value of 0 that we're looking for. So, because our y values jumped from negative to positive, somewhere in between, I know that they had to equal 0. I wasn't able to say that just going from f of 0 to f of 1 because the y values were -1 and -1, and 0 is not in between those two y values. So that really didn't end up being helpful at all. But these two were important because we went from a negative to a positive y value, and 0 has to occur somewhere in between. So I didn't ask a great question here, guys. Is any number 1 less than its cube? The answer to that is yes, and we use the intermediate value theorem to justify that. So if I wanted to write this out formally, I would say yes. There is a number, and we went ahead and called that number c. I guess I should write in a full sentence right here, that is 1 less than its cube. And the reason here would be because, and we would say by the intermediate value theorem, all right, since, what do we know here, guys? Since f of 1 we found was, I guess we could be specific, I was just going to write less than 0, but since f of 1 equals -1 and f of 2 was equal to 5, then we can say that f of c must equal 0 for some c value in the closed interval here. Actually, it's really an open interval as I think about it, although it doesn't really matter, in between the x values of 1 and 2. All right, so that's a pretty decent answer to that question here, and we've named the theorem that we invoked. So everybody, that is how you use the intermediate value theorem to prove the existence of what it is that you were looking for, okay? Now, notice though, we didn't find it in a very tight range here, everybody. We have this thing from 1 to 2, and that's really it. So the last thing I want to talk about, I didn't even bother really writing it out, is something called the bisection method. And what the bisection method does is it allows you to take the concept of the intermediate value theorem a little bit farther and bisect your interval in order to figure out the existence, or I should say the location of this value c with a little bit greater degree of accuracy. So here's essentially what we're going to do. Right now, guys, what do we have here? We have, and I am going to go back to this table that I kind of said not to do before, but let me show you why and what we're doing right here. So here's what we know. When you put in an x value of 1, our f of x value, and by the way, this is all in reference to that function we were just working on. I'm just going a little bit further with example 2. So that was x cubed minus x minus 1. When we put in a 1, I believe we got negative 1. And I'm going to go way down to the bottom of this table now, and when we put in a 2, we got a 5. So we know that there's a y value. I'm going to move this, so you might not want to put this in your table right now, guys, but we know there's a y value 0 that happened at an x value called c, and right now we know that c had to be somewhere in between 1 and 2, but I don't know where. I don't know if c, oh, I thought those would work together. I don't know if c was really, really close to 1 up here, or if c was really, really close to 2. I just don't know yet. So let me move this off to the side for a second, and what we're going to do now is use the bisection method to bisect our interval. Now right now, our interval goes from 1 to 2. It's got a width of 1 unit. And we're going to bisect that by picking the midpoint between 1 and 2, which is 1.5. And we're going to figure out the y value here that goes along with this. Now, once we start putting decimals into polynomial functions, that gets a little bit messy, so we're going to run to the calculator. And I'm going to show you guys something new here. Not that you should do it this way, I just want to show you that you can. What we're going to be doing here, everybody, is evaluating the same function over and over and over again. So it certainly wouldn't be a bad idea to hit menu 1, 1 and go ahead and define this function as x cubed minus x minus 1. One other trick you can do though, and this will come in useful on occasion this year, this is another way to do the same thing in your calculator. I'm going to leave out the f of x and I'm just going to type in the function as it existed, or the expression I should say, x cubed minus x minus 1. And then, if you now want the calculator to evaluate that expression at a particular value of x, here's another way to do it. What I'm going to do, you guys, is hit Control, and then directly underneath it, the second function of the equals button gets me to this menu right over here, and the last thing in that menu, in the bottom right corner, is just this vertical line. And we will use that later in this year when we start doing integrals, everybody. What that is called an evaluation bar. What it's telling the calculator to do is to take the entire expression that precedes that evaluation bar and now evaluate it when x is equal to, and we wanted a value of 1.5. And when we do that, that's what happens, everybody. It took that 1.5, it plugged it into that function, and it got us 0.875, which everybody knows is 7/8, but we'll just go with the decimal right here. Okay, so a 1.5 got us a 0.875. Now, what in the world does that tell us? This value, this ordered pair of C0, it either goes here or it goes here. Now, which one is it? Where I have it right now is not correct. I should say it could be correct, but I don't know for a fact that it is, because right here, your y value was positive, and down here, your y value is still positive. So there's no guarantee that this y value had to equal 0 somewhere in between 1.5 and 2. But if I do this, now I feel a little bit better. Why? Because my m value now is negative, my n value is positive. And a function's value can't change from negative to positive without equaling 0 somewhere in between. So where are we? We now know that C has to be located somewhere between the x values of 1 and 1.5 because that's where we saw the sign change in our y values. So now, instead of where we were 5 minutes ago when we said, okay, yes, there has to be a number, and I know it's in an interval from 1 to 2 with a gap of 1 there, now we've bisected that interval and we've done a better job of locating it. Now we can say that we are on the interval here, that C exists somewhere on the interval from 1. So we were from 1 to 2, but now we're from 1 to 1.5. We've now bisected the width of this interval, and we know the location of this number with a greater degree of accuracy. All right, and guess what? We're going to do it again now. I'm not sure if this C is closer to 1 or if it's closer to 1.5. So let me clean some things up here just a little bit. Let me get rid of that and that and that. And this isn't going to look perfect here, guys, but I'm going to move this down. I'm going to move that down a little bit to give myself a little more room. And what we're going to do now, let me put that off to the side. We're going to bisect this interval now again. I'm going to put a 1.25 right there. And then back to where I was on the calculator, the only real benefit to doing what I did before is now if I hit the up arrow twice, now it's pretty easy to change that 1.5 into a 1.25. And what do we see now? A negative y value. 0.297 is what we would round that to, negative 0.297. So now the question becomes, where is the sign change in y? Is it up here? Nope. We went from negative to negative. The sign change in y is right here where we went from negative to positive. So now I know that C has to be located in between 1.25. That's my new A value, and 1.5 is the B value. So now we've located C within an interval width of just 0.25, just a quarter. And just for fun, guys, we're going to do this one more time. In between 1.25 and 1.5 is 1.375, which is 1 3/8. So let's do all this again. So back up to it, enter, and let's change that 1.25 into a 1.375. And here we get a positive y value again. 0.225, 0.225. Okay, so let me get rid of that red arrow. And now, where's the sign change? Well, it's not right here. That's from positive to positive. The sign change now occurs right here, going from a negative m value to a positive n value. So this is a little crammed, but I now know that the 0 goes right there, everybody. So I can now say that C is located, more specifically, on the interval from 1.25 to 1.375. And we've now found its location down to an interval width of just 1/8 of a unit. And we could continue to do this over and over and over again, you guys, until we got this thing to a level of precision that we felt comfortable with. Okay, so I didn't really ask a question right here, but if something like this shows up on your Chapter 2 test later on, it will say something like, use the bisection method repeatedly to find the location of this number down to an interval of, well, if I said an interval of 1/4, that would have been my answer. If I said within an interval of 1/2, that would have been my answer. And if I said within an interval of 1/8, that would have been the answer. If I say 1/16, you're going to have to do this again. Now, real quick, just to tie this other thing off with a bow right here, if we really wanted to know what was going on, I could have gone here, oh boy, let's do this. Let's go menu, let's go algebra, and let's solve an equation. Way back to the beginning of this problem, we wanted to know, is there a number, x, that is 1 less than its cube? X cubed minus, whoop, forgot my minus right there, minus 1. That's the equation we were trying to solve. Now my CAS calculator will do this for me. So if I tell it to solve that equation, don't forget at the end the comma and then the X, and I hit Control Enter, it finds the solution for us at 1.325 is what it looks like. Now if we go back to our answer that we came up with, doesn't our interval right here include that value that we just came up with there of 1.325? Sure enough, that value is greater than your A value of 1.25 and less than your B value of 1.375. So this is something that really isn't as useful anymore as it used to be back in the day, but some lesser calculators that are still out there right now, like the TI-84, still have programmed into them some type of algorithm that uses this method, and that's how simpler calculators will be able to get you this value from a graph, everybody. It wouldn't do it from the main screen. Okay, so that's a wrap on section 2.8, everybody. That's the last section in chapter 2. So now it's review time to try to get everything under our belts here and wrapped up and ready to go for that test later on this week. So good luck with everything. Let me know if you guys have any questions, and good luck, guys.